Good morning students. Today is lecture 17 of the module 6. So, in today's lecture we will cover high pressure, low pressure RO, advantages of RO, then different applications of the reverse osmosis process, what are the fouling that is being encountered in RO, and how to overcome those. Then we will try to learn what is pressure retarded osmosis and the various applications of forward osmosis. So, as the name indicates high pressure and low pressure RO, it is quite clear that they are differentiated based on the size of their work pressure. That means, what is the pressure that is being applied to achieve this targeted separation, that actually differentiates between this high pressure and low pressure RO. So, high pressure RO has high working pressure, high desalting rate and little water yield. So, in high pressure RO, the operating pressure for the feed side exceeds 100 bar. To achieve high water recovery in wastewater treatment, RO systems that can operate at transmembrane pressure difference of 120 to 200 bar have been developed. Now, high pressure difference help in separation of water from brine with high osmotic pressure by providing a sufficient net driving force. So, high pressure RO is basically used for mainly for the desalination of seawater. Now, in low pressure RO, normally it operates at low transmembrane pressure. So, it is less than 100 bar. So, under this pressure the desalination rate is not very high, however, the output of water is actually large or high, you can say. So, as a consequence, low pressure RO's energy consumption is very less. Low pressure RO finds application in preparation of electronic grade water, which is used in electronics industries actually, where high separation of salt and low molecular weight organic solute is required from very dilute solutions even in ppm range. Now, low pressure RO reduces the equipment as well as operation cost and has its own advantages. Now, they are extremely effective in separation of certain organic and inorganic solutes. More applications of low pressure RO are found in pharmaceutical industry, beverage production, wastewater treatment of food processing industries, etc. Now, let us understand the different design and operating parameters that affect the overall performance of the reverse osmosis systems. The first one is pressure. Now, pressure is the most important parameter. So, we know that water flux depends upon pressure differential between the applied hydrostatic pressure and the osmotic pressure across the membrane. So, with increase in pressure, the solute rejection increases as the solvent flux increases, but not the solute diffusion. So, next is temperature. Increase in temperature decreases the viscosity, which eventually increases the solvent flux. Solute passage has a higher activation energy at high temperature, as like the solvent passage, that results in low solute rejection. Apart from pressure and temperature, there are other parameters which affect the performance of RO are solute concentration. So, high solute concentration causes high osmotic pressure difference that decreases the flux. So, at a low feed velocity, concentration polarization occurs near the membrane, and as the velocity increases, mass transfer redisperses more of the polarized solute that decrease the salt concentration near the membrane. So, that means basically when the concentration polarization is built up slowly gradually, and you are increasing the velocity of the feed. So, this feed actually washes away whatever the concentration polarization build up has already taken place. So, thereby decreasing the solute concentration near the surface of the membrane. So, the next parameter is membrane packing density. This is one of the most important parameter. So, you can define membrane packing density as the unit area of a membrane that can be placed per unit volume of pressure vessel. So, the higher value of membrane packing density, higher will be the overall flow through the system. So, the next one is recovery factor. Now, it represents the plant capacity and lies in the range of 75 to 90% usually. So, high recovery factor signifies a higher salt concentration in the process water as well as in the brine. And then the next parameter is feed water stream velocity. High velocity and turbulent flow are desired to minimize concentration polarization, that is what I just told on the earlier slide. So, and velocity is in the range of 1.2 to 76.2 centimeters per second are normally used. High velocities are used in plate and frame system, whereas relatively low velocities are used in hollow fiber systems. Now, let us understand what is osmotic pinch effect. This is important for osmosis and reverse osmosis systems. So, when a feed solution flows through a membrane array, due to friction effect, a loss of sensible pressure occurs. So, due to friction actually some pressure drop is occurring. So, as water permeates to the membrane, salts start to accumulate, due to which osmotic pressure increases. The highest salt concentration occurs at the exit of the membrane train, the point at which delta P minus delta pi is minimized. So, that point is called the osmotic pinch, and the point is backward from which the hydraulic design actually takes place. A lowest quality of permeate is produced at the pinch as compared to anywhere in the array. So, let us understand what are the advantages of RO. So, as you know that RO systems are little simple to operate compared to other systems, other membrane processes. They does not require hazardous chemicals. They are energy efficient, especially when used instead of distillation to produce high purity water. Modular design for ease of installation, reduces water and sewage use costs, can be integrated with an existing membrane filtration system or ion exchange system to achieve up to 80% range water cycle. So, now let us try to understand and learn different types of applications of RO. We will discuss 2-3 different applications. So, there are many. So, RO is used to produce highly purified water for drinking water systems. Okay, industrial boilers for water, food and beverage processing industries, cosmetics, pharmaceutical production, seawater desalination and many other applications. So, today industries rely on a continuous supply of high purity water to achieve their mission. Reverse osmosis is often part of a complete treatment system that includes pre-treatment and sometimes post-treatment polishing by ion exchange. You can see one schematic representation here. So, the raw water is how actually the water is getting purified. So, water is initially filtered using the coarse filtration system. So, you remove different types of suspended materials, grids and all these things. Then it goes to another process this one tank where the chlorine is being removed. Okay, because chlorine presence is very bad for the most of the membranes. So, chlorine has to be removed. Okay, so, once the chlorine is removed, then it goes for fine filtration, okay, to remove other TDS and other things. Okay. Then next is it goes to the RO system. So, once it comes out from the RO system, so sometimes it requires that there are certain ions which has come out or are being present. So, that needs a further polishing using usually ion exchange, or otherwise RO itself produces very high quality of pure. So, it depends upon what is the intended application basically. Let us see this particular application. This is seawater desalination, which is one of the most important and widely adapted RO application. So, RO membrane seawater desalination system removes salts from seawater to supply fresh water for drinking and industrial uses. So, it ensures supplies of drinking water and domestic water on offshore islands. Desalination of water with a high salt concentration and well water near the seashore is also possible. So, this is a classic example of reverse osmosis desalination system. This is proposed by a company called Toyobo, which is a leading manufacturer of the RO systems. So, you can see what is happening in this particular scheme. So, seawater is coming and there is some pre-treatment occurring here. Okay. So, this pre-treatment, as I told, it is usually remove your suspended particulates and all, then it goes to a tank. So, filtered seawater basically. So, then you use a feed pump, okay, to pump it to the RO systems. So, in between we have different types of protective filter to remove again. So, if at all any suspended materials is there or large molecular weight compounds are there, it will remove it. Then again it you use another high pressure pump to feed it to the RO system. So, this is your RO system, right. So, here actually what is happening, so this high pressure pump is required to supply the delta P, that is required to do the RO. So, when the RO membrane will desalinate the this one seawater and you get fresh water as the permeate. So, whatever the retentate is there, so that is nothing but the concentrated seawater. So, that again comes to something called a energy replacement system, where energy is actually many times energy is required to be recovered, okay, using certain specialized systems. right. So, part of that can again be recycled back to the RO system, because kindly note that this is a continuous system. So, you have to maintain the feed the amount of the feed you are feeding, actually that needs to be maintained, and the concentration if you maintain also, then you can run the system for more time, okay, and you finally get your concentrated seawater here, which can be rejected. The next application is actually again taken from Toibo. So, this is seawater concentration system. This is used to produce actually salt. Okay. So, this particular process is producing salt actually from ocean water and seawater. So, this can help to reduce the load on salt making machinery, lower energy cost and improve production efficiency. You can see this seawater is coming here, okay, and is being feed to a RO system. This is the RO system here, okay. So, whatever fresh water you are getting, okay, so that is basically your permeate side, and whatever you are getting here is the wastewater, okay. So, that is basically the concentrated side, right. So, this concentrated site actually you are you use it basically to produce salt. So, what is happening in this process is this RO is enriching your concentrated this one sea water to more concentrated water. Okay. So, there will be basically the aim is to increase the salt concentration in the water, so that it can easily be resulted into the salt. So, more salt can be produced from the sea water or concentrated sea water, rather than using the usual sea water, which is usually at 35,000 ppm concentration. So, if you can make it to more than 1 lakh, even more than that ppm, then the production of salt, the rate of production will be higher basically. So, this is another classic example of RO in a boiler feed water system. So, here the RO system is being used to produce boiler feed water, right. So, you can see this feed storage tank is there, from where feed pump is there, okay. So, this pump is feeding water. First there is a so it goes to the chlorination unit here. So, where the dechlorination is happening, then it goes to different types of media filters. First is the multimedia filter is there, it will remove the suspended solids and other things. Then it goes to activated carbon filter, it will remove any other even ions which are not required and other low molecular weight compounds also. Then you can add an anti-scalent here, right. So, which will reduce the scaling formation inside the RO system, then finally it goes to the RO system, okay. This is taken from Pure Aqua, a company again leading manufacturer of RO systems. Then you get a permeate water storage tank. So, this goes to the boiler feed. So, please remember this this also produces very good quality of water, though you cannot directly use it as a potable water, it may need some polishing technique, but boiler water, the main thing is that it should be removed of any such ions which form scales, otherwise the boilers will get will have lot of scale formation. So, their operation will become difficult. So, reverse osmosis system reduces the dissolved solids that leading to scaling, as I was telling na. So, the main use of here RO is to remove the scale formation solids. So, removing these contaminants improve the boiler efficiency and increases its ability to work at full capacity. The right RO system design would utilize the ASME pressure vessels, filter tanks and high quality instruments such as conductivity, pH and ORP meters. Having a RO system as boiler feed water treatment can reduce fuel cost through lower heat losses and increased boiler cycles, reducing the total dissolved solid. This is another very important thing in the RO product water, can increase the boiler cycle of construction as much as TDS and anti-scale formation compounds you are removing. So, you are basically increasing the life of the boiler. So, improve operation and steam purity because of the availability of better quality of feed water to the boiler. So, the quality of steam becomes very good actually. The amount of boiler feed chemicals required to prevent condensation corrosion is less due to lower alkalinity in the boiler make of water. So, another example which is also very famous in process industries is the beer de-alcoholization process. So, what is being done is that in nowadays in many of the western countries, people are not at all liking beer as it comes with little higher alcohol percentage. So, they need most of the times when they are preferring actually basically a less amount of alcohol in the beer. Okay, but however, at the same time the fragrance or the taste of the beer needs to be maintained. So, that is another thing actually when you are going to so that is to be taken care of when you are going for de-alcoholization. So, a pressurized beer 2 to 20 to 80 bar is actually put in contact with a semi permeable membrane. Okay, here this is a RO unit, right, to promote the permeation of alcohol and some water to the permeate side. So, that means here the permeate sides some water and alcohol is getting come. So, water is coming along with that alcohol is coming, but one of the disadvantage in that this particular system is actually, so it becomes a costly process RO system, and you need a high pressure. So, that is one of the most important thing that has to be taken care when you calculate overall process cost. So, larger molecules such as aroma and flavor compounds, so they virtually remain in the concentrated side. So, the amount of water lost is typically recovered and added to the feed or at the end of the process for adjustment of the ethanol content in the product. So, how much actually alcohol percentage is required? So, you can prefix it. So, accordingly you can go for one stage process or two stage process or even multi stage process to achieve that, okay, where thereby retaining the flavor and the taste of the beer. So, there are certain miscellaneous applications of RO is also existing. So, RO can be used for recovery of valuable products from wastewater streams. Some specific applications include treatment of electroplating range waters to recover heavy metals, okay, in which the treated water attains suitability for reuse. So, removal of metals from cooling tower blow down water, which is at high TDS as well as 15 to 20 ppm chromates, purification of pulp and paper industry effluents. So, nowadays as you know that most of the process industries water, or we can call it wastewater, definitely contains some of the things. So, either metals, heavy metals, then your different types of ions or even some organic compounds. So, if since the amount of free water that is accessible to most of the industries is getting decreased day by day. So, it is the need of the hour to treat the water whatever it is coming out from the process stream. So, those the idea is that if you treat it, then you can get a better quality of water so that the water can be recycled and reused. So, we need to so then this one need to have more amount of fresh water will eventually decrease. So, that is actually the basic aim of in most of the industries nowadays. So, let us now understand the fouling. We have discussed fouling during microfiltration and all. So, the same process actually how the fouling occurs. So, initially the concentration polarization will occur. So, that means the buildup of these solid molecules, you can see different size molecules are getting deposited on the surface of the membrane. Some solutes will block the pore of the mouth. So, you can see this okay, they are blocking it partially here, okay, and some solutes which are smaller in size that of the pore mouth which eventually get inside the pores, and if the passage is constricted. So, if you remember I showed something like this, if passage is something like this, it is very constricted, again it opens up, okay. So, they will get deposited in this particular area even if the pore is open from both sides, and now this becomes a dead end pore. So, this particular pore now becomes fouled. Okay. So, membrane fouling is the main cause of permeate flux decline and the loss of product quality in RO systems. In not only RO, in all systems, even whether it is microfiltration or ultrafiltration, the permeate flux declines basically due to the fouling or the concentration polarization buildup. So, fouling control dominates RO system design and operation, because most of the RO system they operate continuously, especially the desalination things. The cause and prevention of fouling depend greatly on the feed water being treated, and appropriate control procedures must be devised for each plant. In general, sources of fouling can be divided into four principal categories. So, they are scale, silt, bacteria and organic compounds. So, more than one category may occur in the same plant. So, that is also possible, especially when you are talking about the desalination of seawater. So, seawater contains so many compounds. Okay. It has the scale forming compounds, it has silt, it has bacteria, it has organic compounds also. Okay. So, let us see one by one these different types of compounds that are responsible for the fouling. First one is the scale. So, scale is caused by precipitation of dissolved metal salts in the feed water on the membrane surface. So, the proclivity of a particular feed water to produce scale can be determined by performing an analysis of the feed water and calculating the expected concentration factor in the brine. So, you need to calculate the recovery rate as well as concentration factor to understand how much scaling can be possible using a particular seawater, or you can call it feed water basically. The ratio of product water flow rate to feed water flow rate is called the recovery rate, which is equivalent to the term stage cut used in the gas separation membranes. So, salts that most commonly form are calcium carbonate, calcium sulphate, silica complexes, strontium sulphate, etc. So, your recovery rate is given by product flow rate by feed flow rate, and concentration factor is 1 over 1 minus recovery rate. Scale control is complex. The particular procedure depends on the composition of the feed water. Since the feed water composition varies, so that is why the scale controlling is complex phenomena. Fortunately, calcium carbonate scale, by far the most common problem, is easily controlled by acidifying the feed or by using an ion exchange water softener to exchange calcium for sodium. So, alternatively, an anti-scalant chemical such as sodium hexametaphosphate can be added. So, this will help in reducing the scale formation. It will bound to the scale forming compounds, and those can be removed or recovered from the feed water. So, anti-scalants interfere with the precipitation of the insoluble salt and maintain the salt in the solution even when the solubility limit is exceeded. So, polymeric anti-scalants are also nowadays available, sometimes in combination with a dispersant to break up any flux that occur in the feed water. So, the next is silt. So, silt is formed by suspended particulates of all types that accumulate on the membrane surface. So, typical source of silt are organic colloids, iron corrosion products, precipitated iron hydroxide, algae and fine particulate material. So, a good predictor of the likelihood of a particular feed water to produce fouling by silt is the silt density index. It is called SDI of the feed water. Now, this you can see this figure. This is the silt index density index test, how it is being conducted actually. So, please see this particular equation. This equation is used to calculate the SDI, the silt density index. So, SDI equals to 100 in bracket 1 minus Ti by Tf divided by Tt. So, what is Tt? Tt is the total elapsed test time, either 5, 10 or 15 minutes. So, this you can fix actually, right, and Ti is the initial time in seconds required to collect 500 ml of the sample, and Tf is time in seconds required to collect 500 ml of the sample after the test time Tt, normally after 15 minutes. So, what is the meaning of this? So, you please you can have a look in this particular figure. You see that usually a 0.45 micron filter, not necessarily millipore filter, it can be a millipore filter also being utilized, okay, and you are pushing water through this seawater, right, and you are measuring the volume here using the stopwatch. So, how do you measure? So, the first is that the Ti is the first you start the time and see that or count the time till you collect 500 ml of the initial sample, per minute, basically you are collecting per minute, right. So, whatever the time time it takes to collect the 500 ml of the first per minute sample is called Ti, right. Now, what happen? The second thing is that again you give it some time, then again you start collecting the 500 ml of again the second per minute for 500 ml, okay, after 15 minutes, and that time required to collect the 500 ml per minute is given by Tf, and Tt is the total elapsed time. It can be either 5, 10 or 15 minutes depending upon what procedure you are adopting. So, an SDI of less than 1 means the reverse osmosis system can run for several years without colloidal fouling. So, an SDI of less than 1 is usually better and recommended. Okay. So, an SDI of less than 3 means the system can run several months between cleaning, and SDI of 3 to 5 means that particular fouling is likely to be a problem and frequent and regular cleaning will be needed. So, now you understand what is the importance of SDI basically, and why should we measure it. An SDI of more than 5 is unacceptable at all, okay, and indicates that additional pretreatment is required to bring the feed water into an acceptable range. So, it is understood that you cannot simply feed the sea water or any such feed water to a RO system without understanding what is its composition. So, that will foul the membrane and you will get nothing out of the RO. So, all ROC units are fitted with a 0.5 micron cartridge filter in front of the high pressure pump to avoid silt, and this is silt actually, and but a sand filter sometimes supplemented by addition of a flocculating chemical such as alum or cationic polymer may also be required. So, next category of the scale formation or fouling problem is due to the biofouling. Okay, biological compounds. So, biological fouling is the growth of bacteria on the membrane surface. The susceptibility of membranes to biological fouling is a strong function of the membrane composition. Cellulose acetate membranes are an ideal nutrient for bacteria and can be completely destroyed by a few weeks of uncontrolled bacteria week. We have discussed this thing when you discuss the membrane material characteristic features, properties. So, that time we have discussed that cellulose acetate or cellulose derivatives are not at all good for biofouling tendencies, because the bacteria which will deposit on the surface of the membrane, they will try to use the cellulose as their substrate for their own growth. So, therefore, feed water to cellulose acetate membranes must always be sterilized if you are using cellulose acetate membrane, but again you are adding extra cost to the entire process. So, polyamide hollow fibers are also somewhat susceptible to bacterial attack, but they are less prone with comparison to the cellulose acetate membrane. Thin film composite membranes are generally quite resistant, because anyway you have a asymmetric structure, and periodic treatment of such membranes with a bactericide usually controls biological fouling. So, organic fouling is the attachment of materials such as oil or grease onto the membrane surface. So, such fouling may occur accidentally in municipal drinking water systems, but is more common in industrial applications in which reverse osmosis is used to treat a process or effluent. They are more common in refineries, okay, oil in this one, or oil manufacturing companies, whether it is eatable this one your eatable oil or the oil for the cooking purposes, or your this one crude oil processing industry such as refineries. So, organic matter is often quite reactive, and the risk that it possesses as a foulant depends upon a number of factors, including its affinity for the membrane material. So, one of the most important thing for these organic compounds is what is their affinity towards membrane material. Okay. So, affinity is depends upon the type of membrane material and of course, the organic compounds properties. So, removal of the organic material from the feed water by filtration or carbon adsorption is required. It can also be avoided by selecting a membrane material that resists adsorption of organic material to the membrane. So, now let us understand how to minimize the membrane fouling. So, you can do it by various methodologies or techniques. So, the first one is optimize the pH and ionic strength of the feed solution to minimize the adsorption or deposition of the feed material. So, you can play with the pH, you can easily optimize the pH by adding acid or alkali required, so that the adsorption or deposition of this one foulants on the surface of the membrane will become less. And select an appropriate pre-filtration procedure or to remove so as to remove the large molecules. So, it is always better. So, you have seen in the two schematic diagrams that we have seen, which were proposed by the Stoibo companies, of the desalination as well as the concentration of the seawater. In both we have seen that there are pre-filters in between. So, the role of these pre-filters is to mostly to remove the large molecular weight compounds, since the pressure of larger molecules or particles could cause a steric hindrance to the passage of smaller molecules through the membrane. select a membrane with optimum pore size to result in good separation performance as well as optimize permeate flux. Then optimize the process conditions, operating conditions. So, this includes the transmembrane pressure and to maximize the flux without introducing more fouling potential. I will increase the cross flow velocity. When the cross flow velocity will be higher, it will wash away most of the deposition on the surface of the membrane, thereby reducing the concentration polarization. So, let us understand what is PRO or pressure retarded osmosis. See, this is one of the classic example of a membrane system in which the membrane system itself being used to generate electricity. Now, how it happens, let us understand and see it. So, if in a typical PRO process, water permeates spontaneously across the semi permeable membrane, okay, from the feed into the pressurized salty water. You can see how what is happening, the river water or the water which is devoid of the salt is being fed to one side of the membrane, and on the other side and this is the RO membrane of course, and in the other side you are feeding the sea water. Okay, so, the sea water is transport is happening due to the chemical potential gradient across the membrane, and the volume and hydraulic pressure of the diluted salty water are consequently increased by this process. So, as the volume is increased and the hydraulic pressure of the salty water is increased. So, this will actually help in generating electricity because it is being fed to a turbine here, you can see this. Okay. So, this enables the generation of electricity when releasing the pressurized water through a hydro turbine. So, the water is at high pressure. So, that pressure will be utilized to rotate the turbine, water turbine, okay, and turbine when it rotates, and you know that that the usual way of generating electricity. Okay. So, let us understand the equations involved in that. So, the water flow at a pressure delta P less than delta pi can be represented by this equation JW equals to A into delta pi minus delta P, where A is the intrinsic water permeability coefficient of the membrane. The power watts or joules per second per unit membrane area is given by E equals to JW into delta P. So, that is nothing but A into delta pi minus delta P into delta P. So, let us understand how you will get a maximum power. So, the power is maximum. So, E equals to E maximum when dE by d delta P equals to 0. So, that delta P equals to 0.5 into delta pi, right. So, which implies that E max equals to A by 4 pi into pi r square. So, the above equation signifies the effect of osmotic pressure on the maximum power. So, more is the osmotic pressure, the more will be the power. So, this is the schematic of the salt concentration and osmotic pressure profiles across the asymmetric composite membrane operator in a PRO system. You can refer to it later on. So, the above equation shows actually the effective osmotic pressure to the maximum power. The process was evaluated on the basis of experiment with existing membranes and seawater as a saline solution. In this case about 1.5 watt per meter square was produced, but as a more concentrated solution used, the energy production will increase drastically. So, other practical problems that are associated with PRO is the osmosis. Now, concentration of the concentrated solution will decrease because of the osmosis, that consequently decreases the osmotic pressure. So, eventually when this PRO is going on, so there is some osmosis is also happening. So, that is creating problem because it will decrease the concentration of the concentrated solution, because we understand that more the concentrated solution, more will be the delta pi, more will be the electricity that is being produced. So, another problems are salt flux and concentration polarization. Now, salt flux actually when the membrane is not perfectly semi permeable, that means let us say R is less than 100%, a salt flux occurs. So, you know that perfectly semi permeable membranes are very difficult to make. So, usually there is a salt flux, however, most of the time we neglect salt flux, the Js, which is usually we consider it as 0. So, this results in due to the salt flux there is a decrease in the osmotic pressure, and when concentration polarization occurs, the concentration at both membrane surface is different from the bulk. The salt flux causes an increase in the concentration in the sublayer, which is considered as a stagnant layer and causes an decrease in effective osmotic pressure difference. So, let us understand a better schematic representation here. Entire process of the PRO, the pressure retarded osmotic, this is a PRO osmotic power plant with continuous and steady state flow. You can see this salty water or sea water is being pumped to a pressure exchanger, then from where it coming to the RO system, PRO systems in from one side, and from the other side fresh water is being pumped here. Okay. So, fresh sea water is coming in this direction, fresh water is coming in this direction, and there is a membrane in between. Okay. And what is happening, the fresh water at low or no pressure is being actually getting pushed to the salty water side or the concentrated water side, thereby increasing the volume as well as the pressure of the salty water. So, whatever the salt water is coming out here, so they are not at all high, more concentrated, but at but also at elevated pressure. So, now that elevated pressure or concentrated is being fed to a turbine which will generate electricity, and we get a brackish water here. Okay. Now, most of this brackish water again can be fed back, okay, to this system, okay, mixed with the feed basically. So, the feed streams is penetrated via various filtration in order to remove impurities and reduce membrane fouling. So, most of the impurities which are present that has to be removed for a continuous operation. So, after that the treated salty water is pumped through a pressure exchanger before entering into the high pressure compartment. At the same time, pre-treated fresh water is supplied to the other compartment at no or low hydraulic pressure on the other side of the PRO membrane. The salty water faces the active layer of the membrane, while the fresh water flows against the porous membrane support. With the aid of the driving force delta pi minus delta p, it will be, okay, across the membrane, water spontaneously transports through the membrane from fresh water to salty water. Once the permeate water flows through the membrane, it results in an increase in the pressure in the high pressure compartment. In addition, salty water is expanded with additional incoming volume from the low pressure compartment, and as a result it is diluted to a new solution termed as the brackish water. We are calling it brackish water because eventually its concentration is getting decreased. So, the brackish water is split into two streams. One is to drive the hydro turbine to produce electricity, and the other passes through the energy recovery device, that is the pressure exchanger basically, to recover the energy. So, the pressure exchanger transfers the pressure of the brackish water to the feed salty water, thus enabling a cost effective PRO system. So, this is how a pressure retarded osmosis is being utilized to generate electricity. Now, see, you can understand that the generation of the electricity through this particular system is quite low as compared to the generation of electricity with other processes. Okay. Now, however, if we can generate electricity while thereby whenever simultaneously we are carrying out desalination of seawater or brackish water, then why not? It is always a win-win situation. So, you can see this particular scheme figure, you can see this the amount of free energy could be released is strongly dependent on the salinity difference between the two mixing solutions, right. So, what is the concentration of the salt inside the seawater or the concentrated solution solvent, and what is the salt concentration in the fresh water. For example, approximately 0.75 kilowatt hour of energy could be released when 1 meter cube of fresh water flows into the ocean, assuming a 0.55 molar sodium chloride concentration, which means that 1 meter cube per second of flowing fresh water can potentially produce 2.7 megawatt power. So, you can see here maximum energy that could theoretically be extracted. This is theoretically be extracted from the mixing of fresh water with salty water from different, and there are different things, sea water. So, this is SWRO bind, this is salt dome, a Great Salt Lake, then the Dead Sea. You know the Dead Sea near Israel. Okay. So, you know the concentration of the salt is much higher than any other sea. So, that is why you can see this theoretically more power can be extracted. So, let us now understand what is forward osmosis and what are its applications. So, nowadays forward osmosis applications are increasing because of the simplicity in operation and low energy consumption in many industrial processes. So, let us try to understand what is it. So, forward osmosis is the process of spontaneous water diffusion across a semi-permeable membrane in response to a difference in solute concentration. So, this is how osmosis takes place. We have already discussed it many times. In forward osmosis, the water molecules from saline water move through the semi-permeable membrane toward the draw solution, which is maintained at a higher concentration than the feed solution. So, FO mainly uses the osmotic pressure gradient and not the hydraulic pressure gradient. So, this is your usual arrow. So, when you have to apply a delta P to overcome the delta pi. So, in forward osmosis, water molecules spontaneously move from water to saline water using this semi permeable membrane. The liquid level of the saline water will be elevated until the liquid level pressure difference between two sides is same as the osmotic pressure difference. So, delta pi becomes delta P becomes delta pi. Okay. So, everything is happening due to this delta pi. Okay. We are not pressurizing the system like in case of in case of RO. So, if the water is replaced by the draw solution with lower chemical potential, water molecules spontaneously will move from saline water to draw solution through the semi permeable membrane, which is still the FO process. The feature of forward osmosis is the process driving force just coming from chemical potential difference, but no outer force. There is no outer force is being applied here. The operation is under low or no hydraulic pressure, so that the energy consumption is relatively low. High salt rejection, actually the water recovery rate reaches about 75%, but only 35 to 50% in traditional reverse osmosis processes. Less membrane fouling, because the forward osmosis membrane is hydrophilic. Okay. So, it can effectively reduce the membrane pollution. Equipment is relatively simpler. Low operating temperature also, which is suitable to use the solar energy or waste heat. So, the energy consumption of the forward osmosis system is lower than the reverse osmosis system of the same capacity. So, there are various applications of forward osmosis. The first one is concentration. So, water is extracted by forward osmosis process from a specific feed stream, thereby concentrating it. Continuous extraction of clean water from said feed solutions will result in volume reduction, which in fact concentrates solutes or any other components that is present or we want to concentrate. So, this process is called dewatering. Basically, we are removing water. So, the next is dilution, or it is called indirect water production. So, water is extracted from feed streams by forward osmosis process into a given draw solution. You can see here diluted or feed is being fed to a FO system, and we get concentrator feed here. So, here the concentrator, the draw solution is being fed at the bottom side, and you get the diluted here. So, continuous extraction of clean water into the draw solution will result in volume increase, which in effect dilute solutes and any other components. Then the next application is direct water production. Clean water extracted from feed streams into draw solutions is separated from the draw solutes by means of complementary separation processes, as for example, reverse osmosis, nanofiltration, ultrafiltration, membrane distillation, as well as thermal separations. And it can also be used for the energy production. Another clean water extracted from feed streams into draw solution is used to generate hydraulic pressure on the draw side, which in turn can be used to generate electrical energy via turbines. But anyway, this amount of energy which will be produced by FO will be always much lesser than that will be produced in a PRO system. Okay. So, this is an example of the forward osmosis application. Here you can see this saline water is being fed to the this one forward osmosis process, and this is the semi permeable membrane here, okay, to one side, and the other side we are using a ammonia carbon dioxide as the draw solution here. Okay. So, when you get this is the draw solution tank, actually a recovery unit. So, ammonia and carbon dioxide is being fed to the opposite side, and water from the concentrator, the saline water will diffuse through the membrane, and it will enrich the draw solution here. Then you will get a fresh water and draw solution here basically, and it is the draw solution gets diluted basically. Then you can separate it and take fresh water and separate fresh water from the process, okay, from the stream. And this is another application in which actually the solar radiation is being used to accomplish a forward osmosis system. Again the same process here, there is a semi permeable forward osmosis membrane in which sea water is being fed to the one side, okay, and fresh water which is being fed to this forward osmosis system as a draw solution, okay, is getting enriched or by your water that is diffusing from the saline water to the draw solution side. Solar radiation plays an important role here. So, instead of heating it, instead of this one using any other thermal processes to heat this draw solution, solar radiation can be used to heat it. And then it will come to a tank where you can get the fresh water. So, most of the text is being up today's lecture are taken from Richard Baker, okay, K. Nath, and little from Mulder. So, you can refer these books. Okay. So, thank you very much, and next lecture will be on nanofiltration. So, we will learn what is nanofiltration and what is the transport mechanism and different fouling models and different applications of nanofiltrations. So, thank you very much once again, and if you have any queries, please feel free to write to me at kmohanty@iitg.ac.in. Thank you very much.